Hello everyone, this is Universum, the place where you learn about the entire universe, how it began and how it will end. Today we are going to be talking about the Maxwell-Faraday equations and their solutions to them, and possibly their future applications on quantum electrodynamics itself. In order to start, we first need to get to understand what quantum electrodynamics is and how you can quantize certain assortments of equations. So first, we need to do the Maxwell's equations. First, we need to do the Maxwell's equations. There are about 4 of them. So the first one, they're just letting you know, they can be written in either differential form or they can be written in integral form, just letting you know. Alright, so let me tell you the 4 of them real quick. There'll be Gauss's law for magnetism, Maxwell-Faraday equation, otherwise known as Faraday's law of induction, and Ampere critical law with Maxwell's correction. Now, let me tell you the differential form first. Now keep in mind, if you don't understand this, please skip this part. First, let's do Gauss's law. So first, it'd be del of E. E would be a certain constant that is fluent throughout the equation. That'd be the electromagnetism constant, which then would be equal to a certain type of Planck constant, which then would be divided by epsilon, to the state of 0. All right. So basically, what that is, that would be a certain type of electrostatic force, so a certain type of electrostatic uncertainty presented by differential equations and divergence. So in order to understand the rest of the equations, we first need to get to understand 2 laws of vector calculus, tensor calculus, and many different other types of maths. It would be called divergence and curl. It's really, really simple. And simply what it is that you just take different assortments of unit vectors, and then what you do is that then you just simply put them on a planar plane, and then what you do is that then you trace out a triangle using the different types of hat, or otherwise known as caret functions. And then you use Pythagoras theorem in order to measure the amplitudes, otherwise known as the magnitude of those vectors. So first, let's just do a little bit of a thought experiment here. Here, hold on, let me just go ahead and just get my notebook. Alright, so pretend that this is a plane. Now what I'm going to do is that I am going to be tracing out a plane. So it's going to have an x-axis, and it's going to have a y-axis. Of course, many of you have learned this in school. It's really, really basic. But I guess I'm trying to get into as much detail of quantum divergence law as possible. So now we have basic planes, planar planes, if you will. So then, let's mark this one to be y. Let's mark this one to be x. Whoops, that looked a little bit like a capital lambda for a second. Anyways, so first, what we're going to need to do first is that we are going to need to write out, we're going to need to write out some unit vectors. So let's put 1 at a y-intercept of 5. 1, 2, select there. 1, 2, 3, 4, 5. That'd be 5 on the y-axis. Then let's put another one. Let's put this one at 8. Okay, actually, let's put this one at 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9. There we go. Then now, in order for it not to be scalar, we need to put an arrow to it. This will be very important to know in the future. So then we need to let's call this first one up here. Let's call this one up here I hat, or you guys can call it caret, whatever you guys want. And then let's call this one J hat. All right. Then what we're going to need to do next is that we're going to need to trace out the triangle itself. So what I'm going to be doing next is that then I'm going to be adding a third variable, which then is going to be intercepting along with one of these, creating a planar plane, which then this is going to be K hat. And then this one is going to be scalar, since if it were in motion, then, well, this will look like a chaotic mess. So then, what we're going to need to do now is that we are going to need to draw a convergence line through the center of it. And then boom, you have a basic right angle triangle right out of the blues, just by using divergence. Well, how is it useful? Well, let me show you in a second. So now by applying Pythagoras' theorem, so we could do a squared, then we could do b squared, and then the hypotenuse would be c squared. Sorry if you guys can't see that. So then if we measure the amplitudes of that, we could, in theory, measure up all of the amplitudes of all the hat functions. Now, the reason why this is useful is because by using different assortments of unit vectors, what you could do with them is that you actually could create different types of field lines. So first, let's get into divergence real quick. Divergence basically will be the certain assortment of unit vectors going throughout a graph. So let's say if there was a vector right here, a vector right here, and so on and so forth, all going out forever. But although there is but not necessarily forever. There's not an infinite amount of them, but there's an extremely large amount of them, all converging around one singulative point, the origin. Now, also by measuring up the amplitudes of these different types of functions, we also can measure for the function of theta, which then would be the center of the functions. So then, what we're going to need to do next is that then we are going to need to do a little bit of complex math here. All right, so in fact, I already have written out an equation for this. We're finding out the value of theta. So then, what we're going to need to do first is then we are going to need to be. All right. So first, let's do this equation right here. This will be the vector addition function. This is what it means. This would mean two scalar functions, a plus b, really simple, which then would be equal to times a sub x plus b sub x, which then would be times I hat or I carets. I'm just going to call it I hat for the rest of this video in case you don't mind. And then this would be plus the function, this would be plus and times the function of a sub y plus b sub y, which then would be times x, which then would be that again multiplied by j hats. This basically just applied all functions together, so then you can find out the exact values of those functions. Now, of course, in case you doesn't notice down here I actually wrote the Bra and Ket version, which then would be represented by a Dirac notation. Basically, the Dirac notation would be representing different types of functions that are strewn throughout the Schrödinger equations. Now, a Bra and a Ket function, what those would be is that those would be different types of eigenstate values in the form of a divergence and curl law. Now, I've been saying a lot of divergence lately, but exactly what is it? Well, that's what we're about to get into. So hold on to your hats. All right. So first we're going to need to be doing the first two divergence equations, which then would be del, which then it would be the derivation function, which then it would be times e, which then would be a unit vector, which then would be a certain type of vector function, which then will be plus the same type of constant that we saw before, which then will be divided by epsilon. And then another equation, which then will be del, again, a derivation function, which then would be times b, another type of vector, which then would be equal to 0. And then for number 3, now these other two are going to be for curl. These are going to be two curl equations. It is going to be del times e. E is going to be a certain type of vector function, which then would be equal to negative differential of b. That would be the b vector that we just talked about a little bit earlier today, which then would be divided by the derivation or the differential if you're a differential enthusiast of time, which then the other equation would be the del function of times b, as we just said before, which is in the last equation, which then it would be also, then again, a vector, which then would be equal to u sub 0, which then will be times j, another type of vector variable, which then, oh, what do you notice, some of you physics enthusiasts? J hat. All this is because due to not being a hat, thus making it not a scalar function. So then, that would be plus 1 divided by c squared. That would be the speed of light. Then that would be a certain type of function, which then will be represented by bosons, which we'll get onto a little bit later when we get a little bit deeper into quantum theory. Which then that would be multiplied by the derivation value of e, of course. That would be another function. In fact, there actually is a function for this, which then will be e to the ikx. Basically, that would be just a good old function that would be from the k hat, would be from the I hat, j hat, k hat functions, which then would be divided by the differential of t, which then that's then c. First, let's find out the value of c, even though it's the speed of light constant, which then would be equal to 1 divided by the square root of u sub 0, which then would be times epsilon squared. Now, you're probably wondering, what is all this function? Well, I'm about to explain it to you. So all these different types of functions, all of them together, what they are trying to explain is that they are trying to explain the meaning of the quantum electrodynamic field. It's basically so the way that electrons and photons can move throughout a field, the way that they can curl and diverge throughout a field. Imagine water. Imagine water that's going down a drain. As it keeps on getting closer and closer to declination points, the standard derivation, otherwise known as phi, it gets faster and faster and faster. That'd be a diverging curl of it. And that'd be divergence curl law, which then basically just be all its equations combined together. That all of that could represent these equations all together. All that could represent how the electrostatic and electromagnetic fields could work. Electromagnetic field lines of nature, the way that different differential types of quantum particles could work, the way that photons could be bouncing around my room, and then could be getting bounced right back into my retina. So then I can see these images that I'm seeing right now. It's quite amazing what you can just do with a little bit of vectors. Even though light just seems just so simple, it can be really, really complex at most times. So now, what we also have to go into a little bit more is that we also have to go into a little bit of the way that certain functions could work. So like, for instance, first we're going to need to be going into quantum field theory a little bit in deep detail. So first we're going to need to be looking at all of the particles of matter. So as you know, the atoms, which then will be represented as the Bohr-Einsteinian models of the atoms, which then if you break them down, then you get protons and neutrons. You break those protons and neutrons down, you get elementary particles, which then will be quarks. Then it'll be connected by the strong force, which then will be represented as gluons. And then what would happen next is that then, well, possibly inside of these quarks, there could be these theoretical particles called preons, although they're not necessarily confined. They're not necessarily proven. Then inside of those, there could be an oscillating string factor that could just be vibrating at a differential types of values at a rapid pace. So now, let's go ahead and take a little bit of a trip across it. So first, what we're going to need to be doing is that first, let's look at the different types of quarks there are. The main ones that make up protons and neutrons would be up and down quarks, except for if it is under special conditions. Like, for instance, if it's under a lot of pressure, if it's under barely any pressure at all, if vacuum decay happens, etc. So just letting you know, keep these in the back of your head for the rest of my videos, just letting you know. So 2 up quarks and 1 down quark makes a proton, while 2 down quarks and 1 up quark make up a neutron. Just keep that in the back of your head, okay? It's going to be important later. Then let's get on to the rest of them. There are about 4 more left, or at least 4 more quarks left. So then we get on to strange quarks and charm quarks. So charm quarks, you can find them inside of radioactive matter that is under standard conditions. So in order to radiate away that particle when it's undergoing bremsstrahlung, what it's called. So what it would do next is that it would radiate the particle, turning it into a beta particle. Or if it's a massive enough atom, it could simply just rip a part of the nucleus and just create an alpha particle, a low-charged version of a helium-4 nucleus. Then we get on to the very strange quarks. Yes, they're literally called that. Now, strange quarks, they usually are found in the centers of neutron stars, where all the matter is concentrated, and yeah, they're really, really rare. Although they're mostly found inside of quark stars and strange stars. Now, it would take much, much longer than this video. I don't want to make this video too long. So I'm going to say that. So I'm going to say that for a whole new other video. Then we get into the top and bottom quarks. The top quarks are by far the heaviest. They are the heaviest of all the quarks, and they are found in radioactive matter under extremely compressed conditions. And then we go down to bottom quarks, which are basically the exact same thing. So in the end, we start to notice that quantum theory is quite interesting at the moment. It is much more than we actually thought it would be. And much, much more. Then we bring ourselves back to, then let's go past the quarks, and then let's go into leptons. Now, leptons, basically, they'd be these particles that are almost in a weird super state of being an elementary particle and a subatomic particle. So there are about 6 types of leptons, as there were 6 types of quarks. So now let me just go say them. Electrons, you know what they do. What they do is that they spiral around the atom and they give the atom their characteristics. Then what there is next is that then there's going to be a muon when under extreme conditions. Basically, it'll be the heavier, faster version of an electron, and they live for about 1/25 millionth of a second. Then there'll be a tau. A tau would be a very interesting particle. There's not much known about them, and then here we stop talking about them. Then there's the electron neutrino, muon neutrino, and tau neutrino. Basically, these are just different types of neutrinos and what they could do is that they're so small that they can pass the grooves of protons and neutrons as we know it. Then we get on to gauge bosons. There is a gluon, there is a photon, and then there also is a Z and W boson. So the gluon, of course, that'd be strong force interactions. The photon would be the light interactions explained in the equation that I just explained, the Maxwellian Faraday equations, along with some Gaussian equations. And then there are Z and W bosons, and those were just discovered. So then here we stop talking about them. And then there is one interesting one, known as the Higgs boson. The Higgs boson, particles acquire mass by interacting with the Higgs field. It gives things a more stable field by particles interacting with them. What happens is that so let's say the Higgs boson was discovered a few years ago, actually, and I won a Nobel Prize for it. Now, the Higgs boson, what it is it is a scalar type of boson. Now, you know what scalar means. As I said before, it means there's a type of velocity vector on it that cannot move. It is static. It is stationary state. It does not have any sort of SHO on it, other than a simple harmonic oscillator on it, in order to define its certain type of superpositionized states. It simply just makes particles interact with it. We're not sure how small or large this particle is, but we might be sure that it might be in an infinitely recursive superposition of states. Particle theory is quite interesting when you think about it. But the more you know about it, the more you can see patterns, the more that you can see differentials, the more that you can see equations through functions. I hope you guys enjoy my video, and well, I'll see you in the next video.